I'm delighted to have with me R.J. Jones, a research microbiologist with the Cold Regions Research Laboratory, and we're going to be speaking about sparking the electric secrets of soil. Good morning, R.J.
Good morning, Annette. How are you doing?
I'm doing great. Thank you so much for being on the show this morning.
My pleasure. Thank you for having me.
Well, we're just going to dive deep into tell me about yourself and your background.
Of course, always a fun question, although it's like I'm on one of those reality dating shows. But my name is RJ. I live in Hanover, New Hampshire now at the Cold Regions Lab. I like running, video games, trashy romance novels, Korean dramas.
Okay, all right. We're not on the dating game.
No, but
didn't mean to interrupt. It could have got really interesting. I'm sorry. I didn't mean to interrupt. Go ahead.
No, that's good. Salty foods, naps under shady trees. No, that's it. Probably just a cat. But no, I grew up in a large suburb of Arizona around the Phoenix area, and I got my undergrad at the University of Arizona in Tucson, where I studied soil science and crop production. After undergrad, I was a lab tech for a lab that studied the microorganisms in changing permafrost in Abisko, Sweden. And that's where I kind of developed my passion for microbiology and data science, as I was doing a lot of DNA extractions, RNA extractions, proteins, and analyzing the community data that comes from that. But after 2 years of that, I had a bit of a crisis moment because I realized, as many people in their 20s do, that I had no forward plan for my life, and I kind of had a freak out. But so I started looking into maybe graduate school, working in a professional lab and kind of preparing me for graduate school or industry or something like that. And that's when I stumbled upon CRREL and the ERDC. And there was this really cool team that combined my interests, which are soil and microbiology. And I thought, oh, that would be cool to do for a year or two while I, figure things out, get out of Arizona for a little bit. And that was 9 years ago. So clearly something happened. I liked it here. But since then, my research has really expanded to include things like microbial electrosynthesis, biosensors, electrical engineering, mycology, just a bunch of stuff I never thought I would do,
Well, you already sound very passionate about what you do.
Oh, yeah, I try to be.
So what is your role at ERDC?
Good question. I wonder about that all the time. So,
is it ever changing?
It is ever changing. I think all of us wear at least 12 hats at once,
Right.
So I'm at the Cold Regions Lab in Hanover, New Hampshire, as I said, in the Biogeochemical Sciences branch on the soil microbiology team. So I'm really fortunate, actually, to be on this team because I've been given so much support throughout my career, from a junior level scientist to, I would say where I'm at now, I'm mid-career, mid-level maybe. But I started off as a researcher on other people's projects, and now I'm leading my own project as a PI and collaborating with my peers on their projects too. I think my official title is research physical scientist, at least on my W-2, But I always found that's kind of not a useless title, but it's like saying, oh, you're a doctor. It's like, well, yeah, but are you a radiologist, a cardiologist, orthopedic surgeon? So if I had to give myself a title directly, it'd be a research electromicrobiologist. And my self-appointed role is to study the dynamic intersection of electricity and microorganisms, how they produce electricity and interact with electricity and signals as well.
Well, that just opens right up for the first, technical question you might say is, as many of our listeners have probably figured out, ERDC has experts in just about every scientific field you can imagine. I hear that you are one of ERDC's go-to experts when it comes to soil. What sparked your interest in this type of research?
Oh, well, thank you for saying so. I don't feel like an expert a lot of days. I think I've kind of gotten to the stage in my career where I've definitely learned a lot. But I think in learning a lot, I'm able to see how much I really don't know, and I don't know beans in the grand scheme of things. But fortunately, there's a lot of experts, other soil experts at CRREL and ERDC as well, then together we know quite a bit. But I think this all started back in my childhood, to be honest, with this obsession with dinosaurs. I mean, what kid doesn't love dinosaurs? But I was the weirdo sandbox kid. Every day at recess, other kids would be playing kickball and tetherball and out in the field, whereas I was in the sandbox digging for dinosaur bones because I was certain that they were there somewhere, right? They had to be. I really wanted to be a paleontologist when I was younger, so I spent a lot of time digging holes. And I found out as I got older that real paleontologists don't really do what they do in Jurassic Park, dinosaur DNA not excluded.
Hmm.
But I had to kind of refocus, I guess. But since I already had this like passion for soils and in the ground and stuff like that, I kind of went more into environmental studies. So as I mentioned, I went to University of Arizona, which is an ag school, and the Soil, Water, and Environmental Sciences Department. And shout out to them, because I don't know if they still do this. I hope they do. But freshman year, you are kind of obligated to take this overview course that kind of summarizes each of the key areas in the environment. So you study, soil science, hydrology, environmental policy, so all these different things. And it was in the soil science segment that I was like, oh, wait a minute,
A bell went
new.
off?
A bell went off.
That's right.
But I've always been like a hipster at heart, and I love things that like no one else does or like go unappreciated, like the deep cuts. So the more I started learning about soil, the more I was like, how is no one talking about this all the time? It's so cool. Like in a gram of soil, there are more microorganisms than there are people on the planet. And that's just like in a gram. It's flabbergasting. And when you start learning about what it takes for soil to form and like the role it plays in the environment, it's honestly quite beautiful. But I think the thing about soil that really kind of hooked me, and this is going to be a little bit weird, but it's this this thing called the Munsell color chart. It's a book that has all the colors of soil, like that soil can be, and it's way bigger than you'd expect. And in like reading it, you get used to classify soils. You kind of start realizing that wow, this material beneath my feet is extraordinarily complex and unique and diverse. And since it's always there, it's it's always hidden, and we don't really think about it or see or talk about it often. But once you know what to look for, it's honestly quite magical because each soil tells you a little story about how it was formed and has a little history to it that's old as time.
Wow. Okay. As you say, before we go any further, you're usually quick to explain to people that soil and dirt are not the same, even though most of us wouldn't think that there's much of a difference. What exactly is the distinction between soil and dirt?
I'm so glad you asked. Honestly, if I could leave one legacy on this planet, it's like hoping people like just shudder when they think about saying the D word instead of soil. Know that I go feral for it.
And you'll go down for making that happen, right?
I would love to. I know I'm already working on. My parents have they've been re-educated, I should say. They don't say the D word anymore. So no, I'm getting some traction. But all jokes aside, it's really an acknowledgement of two different materials. So I mentioned before in our earlier conversation, like each soil tells a story. That's because soil is the result of a lot of time and environmental processes. It's unconsolidated minerals and organic matter that's been shaped by the environment and like just a lot of time usually. But when you zoom in, it's this like complex material of different particle sizes, your sands, your silts, your clays, organic matter, microorganism, gas, water, and they all come together to support life and perform environmental functions. And I think that's one of the key differences is that soil is part of a system that supports the environment, whereas, I'm going to say it, dirt is just schmutz underneath your fingernails. That technically does support life because microbes can grow anywhere, but it's not this like masterpiece shaped by eons of biogeochemical processes. So really when you call soil dirt, you're mostly just not being scientifically accurate, as dirt is, for lack of a better word, dead. It's stagnant. It's
Right.
not this dynamic process anymore. Whereas soil is still dynamic. It's a lot of things going on in there. It'd be like saying the Grand Canyon is a big hole in the ground, which is like, no, it's a canyon. It's shaped by thousands of years of erosion and weathering, representing a history of river pattern shifts. And as an Arizona native, I spent a lot of time at the Grand Canyon every year of my childhood, whether we wanted to or not. So.
Well, so dirt is just what I guess this is not a technical term. I guess you could say it's icky.
Yeah, kind of. Yeah, it's useless, I would say.
Right, exactly. So I would think most people would be surprised to hear that there is a connection between soil and electricity. Can you explain how they are related?
Oh, I would love to. Honestly, it's one of the coolest things I think I've learned and I get to work on. So I mentioned before that in 1 gram of soil, there are billions of microorganisms. And as you can imagine, there's a lot of diversity in those billions. Same as people on Earth. There's a lot of diversity in the billions of billions people live on Earth. So there are microbes that are harmful, some are pathogenic, some are helpful, and they come in all shapes and sizes. But particular species, groups of species of these organisms are capable of producing electricity, or more accurately, they can produce free electrons, and we call those electroactive bacteria.
Okay. So how do those microorganisms within the soil produce electricity?
So this is really neat, honestly, because essentially what they're doing is quote unquote breathing, not the way we think about it necessarily, but the same process in that they're using something to move electrons and perform chemical reactions. So in our case, we use oxygen, and many other organisms do as well. But these electroactive microbes are, if they're in an oxygen-poor environment, they'll use whatever else they can. And usually what's available in soil, at least, is organic matter. So when they break down organic matter, they're liberating free electrons and creating a charge. So, but what's really cool about these organisms is that they have specialized body parts, like little wires or channels that allow them to transfer this charge somewhere else. Individually, because they're small, there wouldn't be a whole lot of charge involved, but a lot of these organisms can form a biofilm, or like a large aggregation of themselves, like what can clog up your sink and stuff like that. So, and together they're breaking down large amounts of organic matter and producing a greater amount of charge. So this is where the electricity happens, because electrons, when they're moving, that's when actually is considered current flow and electricity. So when these biofilms have a surface to deposit electrons on, and a place with low electrons where they can naturally flow, you can actually start creating a current. Because electrons are like water. They'll always flow from the highest point to the lowest point. In this case, an area of high electrical charge to a place of low electrical charge. So we, the humans, can create those spaces and drive electrical current by giving the microbes in soil a place and environment to grow on. So we create what are called microbial fuel cells by making a circuit in the soil column, pretty much a cup of soil, where we can put a conductive fabric, usually it's like graphite, something easy to obtain, in the bottom of the column where there's a little bit of oxygen, very low oxygen, and that's the anode. And then we put one on the top, which is the cathode, and connect them through a wire with a breadboard, someplace we can actually measure the voltage. So the anode gets colonized by the electroactive bacteria, and they start producing charge when they start breaking down organic matter. And eventually, because the cathode has low charge, the electrons will flow from the anode to the cathode through the circuit and thus produce electricity. So this is the same way that a AA battery works, or really any battery works, except for, in batteries, there's this chemical reaction that's happening that's creating free electrons that are then moving. So things like lithium ion and stuff like that.
Mm-hmm. So if you could see my head, it's blown. So anyway.
I know, sad.
I read that the electrical signals within soil can indicate the presence of environmental pollutants. How is that possible?
Oh, wonderful question. So electroactive organisms that are producing electricity are, breaking down organic matter to create charge. So it turns out like they're not actually that picky about what they use, like what they actually feed on to create the charge in the first place. And there are some really cool studies out there that show these organisms can use a wide range of complex compounds to produce charge. Things like pharmaceuticals, pesticides, even heavy metal complexes. But the question is, how do they indicate whether there's pollutants there or not? So that's what's really neat about these soil microbial fuel cells. So again, this soil-powered battery, more or less, it's that their output is something that we can actually measure quite easily. Like we've been able to measure voltage for a very long time, and like you can go to Home Depot today and get a multimeter that can do it. Mm-hmm. So what we do is just essentially hook up the multimeter to the fuel cell and get the voltage reading. And voltage is just like a level of charge, which in this case is kind of close to representing the microbial activity. So we like to think about the voltage as like the heartbeat of the cell. And as microbiologists, especially environmental microbiologists, we often say that microbes are the first responders to the environment, and that they can like quickly respond and change different environmental perturbations. So imagine how the voltage might change in response to something harmful entering the environment, right? So depending on how microbes respond to it, the voltage may drop because it's something toxic to them, or in some instances, it might actually even get higher because it's the compound that they can utilize. So the point is that they would shift in from what is normal in a way that we can measure very easily. So think about it the same way, like, I don't know if you're a coffee drinker, but, you have a general sense of what your normal level of energy is. But then when you have too much coffee, you're amped, you're ready to go for the next 2-3 hours. And and if you have too much, you might be a little shaky, twitchy, perhaps even a little irritable. I don't know. I know I get irritable without my coffee or too much coffee. Both kind of go. But that's like
I don't know if I
an
can drink too
observation.
much coffee. I'm just saying.
Apparently, the dosage, lethal dosage for caffeine actually is quite high, so higher than you think. But I guess like us, microbes will have some kind of observable output when they have too much of something or too little of something.
Hmm.
You know, in that case, like if they are dosed with something toxic, the observable output may be the drop in voltage. Do they get shaky, so to speak? But for us, the science is kind of learning what environmental pollutants cause what kind of cues, and kind of tracing that back, working backwards and thinking about what is happening on a chemical microbial level. Yeah.
Well, so we've learned that soil can create electricity and warn us of possible pollutants in our environment. Okay, we've learned that. So, as if that weren't enough, I understand that you have also studied ways that soil can help keep our military men and women safe while on patrols. Okay, just wow. How does that work?
Oh, it's so cool, right? I love talking about this, honestly. So, what my colleagues and I are working on is leveraging these electric organisms into functional biosensors, or living sensors, with the help of machine learning. I know AI is really big right now, but we were doing this before AI was cool. I'll say that.
Right.
This all, I think, started with my colleague, Dr. Robin Barbado, who was like, wait a second, we have these environmentally responsive microorganisms found in the soil that can create voltage patterns in response to different chemicals. And we have machine learning algorithms, which are really good tools at recognizing patterns. Like, can we combine these things together? And our research is suggesting that, yeah, probably you can. So what we can do is train machine learning algorithms to read voltage patterns produced by microbial fuel cells in the soil, and then they can recognize when the fuel cell has been disturbed because the voltage will be changed in a unique way. The hard part is understanding how the voltage changes and if it is unique to each pollutant or contaminant. And for that, we need like lots and lots of data. But the goal is to be able to like deploy these microbial fuel cells into the ground in sensitive areas where it might be patrolling, or areas we want to keep like, occupation to a minimum because it's a controlled space.
Mm-hmm.
And we'll have them reporting their voltage to a central microcontroller that's running a machine learning algorithm that's like looking for changes. So when something hazardous leaks into one of the fuel cells, voltage will change, and if we train the algorithm properly, it will say, oh, hey, something's happened. And hopefully, if we did a really good job training it, can not only tell you that there's been a shift, a change, also can tell you what that shift was caused by. If we can kind of demonstrate that let's say it's gasoline, for example. Let's say someone like accidentally spilled gasoline in the area. Does that cause the voltage to shift in a very unique way that the algorithm can pick up? So at the very least, maybe we can have it do a warning level, something like, hey, like all the fuel cells in this area got contaminated and they died.
Mm-hmm.
Like the voltage is gone. So whatever hit them is probably pretty nasty. Don't go over there in that area until we can figure out what it is. So we're kind of playing around with like, okay, how sensitive can we make these? Like what can we push the algorithm to do? And that's the goal, is to get these sensors that are able to warn people of hazards, essentially. But we still need lots and lots of data to make it happen, especially because, we're put them in the environment, and while pollutants is one thing they can interact with, there's just the environment as a whole. There's, shifting temperatures, moisture fluctuations, rain events that can trigger the sensor.
Mm-hmm.
So figuring out how to train the algorithm to understand the difference between, real events, real signals, and just noise. So there's a lot of work to be done, but there's a lot of promise so far. And for will or for woe, AI has gotten a lot better at understanding patterns if it's trained well enough.
Wow. And so, so important. Thank you for what you do.
Oh, thank you.
It's so important. So this year, as we continue celebrating the 25 years ago to form one ERDC, one organization of experts across multiple disciplines, how do you collaborate with other researchers or organizations with your research?
Oh, this is one of my absolute favorite things about ERDC, honestly. Like, we have all the cool kids under one roof, pretty much.
I love that. We need to use that as a new, positioning statement or slogan. All the cool kids.
Yeah, put on a t-shirt.
Exactly.
It's kind of wild. I didn't have a full appreciation for it until I got here, but just how, any one of us can be like, when faced with a task, we're like, oh, I don't know how to do that. but I know someone who can. I
Right.
think it's Gary. And then you go down the hall and to Gary's office, and it's like, hey, can you help me with this?
Hmm.
And I guess the simple answer to your question is I just kind of ask them. Like I can go down the hall over to the next building and just kind of ask the person who has that skill set.
Hmm.
And I think that's truly the power of ERDC because like not only can I do that, like I have the reasonable confidence that that person will either be able to help me or point me in the right direction. That's kind of just the culture here. We're all playing for the same team and have this like shared desire to help the nation. So like for our microbial fuel cell project, we have to assemble a team with like a machine learning expert to develop and train the model, electrical engineer to do all the wiring, interface the controller to the fuel cells, microbiologists, of course, to help develop the fuel cells, and mathematicians to run all the statistics and the math. Like it's every person that we asked, they were like, hey, do you want to help us turn like a soil powered battery into a biosensor? They were like, that sounds really weird, but sure, I'm in. It was great. But honestly, I think we kind of need that level of collaboration, especially in the ERDC, because like what we research is simply just too complex to be like on one discipline. It's so like our problems, like not problems, I guess they are problems that we solve.
Right,
Our
right.
research questions, they take a whole team to understand them, and I think in a broader sense too, the way we collaborate is also becoming invested in each other's research. Like I now that I'm managing projects too, I like just love being a fanboy of other people's research and learning about what they do.
Hmm.
And I think as your listeners probably have figured out by now, like we do some really cool stuff. Like I think, not to toot my own horn, but myself included, but there are some incredible researchers at across ERDC. But me specifically, a lot of my work requires me to collaborate with electrical engineers, programmers, and general engineers. And I think the hardest part is finding that common level of understanding because we all speak different languages in scientific sense. And I think it's always hard, especially because I think working for DoD, we all play the acronym game all the time. It's part of our
Every day.
every day.
Every
But I
day.
think with almost I don't know about other people, but I feel like there's this secret like acronym off to see who can get like the best, coolest acronym, but also has like Project Eagle. Well,
Right.
that sounds cool, but also is scientifically informative.
Like it should stand for something, but yet be a cool word. I totally get it. I totally get
Oh yeah, that is my second goal in my legacy is to come up with a good acronym that sticks.
So we've learned a lot during this conversation about how soil is much more complex than you would think. How important is it to our overall ecosystem? And is there anything the average person can do to preserve the delicate balance?
Oh goodness, I don't think I can overstate its importance, honestly. Like I think, here was it the USDA or the EPA? What year was it? It's like 2018 was the year of soil. Just to highlight just how important and critical it is for the environment. I would say like next to the ocean, it's one of the most critical aspects of our ecosystem for a lot of reasons. But I think probably most directly to us as humans in our life is that we depend on it for food, we depend on it for clothes, our infrastructure in general. I could give a whole lecture series on the function of soils in the environment, but I think the biggest considerations are, nutrient cycling, support of the water cycle, and support of plant life, really all terrestrial life,
Mhm.
and just support of our modern life. And like in soil, again, we talk about how it's everywhere, but I don't think we think about it as often as we should, really. And in that sense, I know it's also hard to think of how one person can really make a difference in, the grand, something so massive, But I mean, all of us can be part of like necessary cultural shifts in changing how we think about soil, how we think about our relationship with it and the environment. And I think the biggest thing you can do is to help preserve the environment in your community, in your home, and support sustainable agriculture. I think that's one of the bigger things that can cause pretty immediate impacts to the integrity of soil. And I would say overall, work with nature, not against it.
Right.
Do your homework and understand the environment you live in. I think a lot of us, especially during COVID, we got into gardening. I definitely did.
Yes.
So it's important to look into plants that are actually native to your area and promote local pollinators and flowering plants. Because a lot of things, like while they're great, it's like, oh man, that actually does not really grow here very well. Actually, if it got out, it could be kind of hazardous to local plants and overtake them. So obviously, don't pollute. I think that one's pretty clear cut. And support sustainable initiatives and something that I think doesn't get talked about enough is just also supporting and respectfully looking into the knowledge of indigenous people in your area. It's like that's a resource that is, like any resource, not an end-all be-all. They don't have all the answers. None of us do. But it's a resource that is certainly undervalued in our modern society and is likely to have more like regionally relevant knowledge about the environment in your area and cultural practices, how they maintained different local plants and what those plants are, you know. So yes, overall, yeah, work with the environment, grow flowers, the pollinators need it, and don't mow your lawn in May. I think that's become like a very big thing. No mow May.
Really? I've never even heard of that.
Well, for here in New England, winter's changing, but you know, by the time May rolls around, there's not actually a lot of most of the pollinators are like desperate for food. They're so hungry because they've had to survive winter. Things like spring has like barely gotten some stuff up for them. So once things are flowering, if you immediately cut them down, the pollinators haven't had enough time to actually get out there and like collect more food. So it's mostly for them. And also, I don't know, the greenery is good.
You're also causing people, when they go to the store during the spring and picking out the soil that they need, I think they're going to be thinking a little bit more about what they're going to get. So,
oh, I hope so.
Yeah, exactly. So I know this is probably the most unusual question the listeners have heard on all 3 seasons of the show. How can mushrooms transmit electrical signals?
Oh, now we're getting into the good stuff.
Yes.
Yeah, honestly, this is one of the weirder things that I think that I've done as a researcher, and not something I could have ever seen coming when I first started working at ERDC. But I guess to make it sound a little less science fiction-y, although it's pretty science fiction-y, really, I'll clarify that what I'm studying is how fungal structures can be carriers for electrical signals. Although I imagine people have seen those videos on YouTube where mushrooms are playing music, which is really cool for sure.
But I haven't seen that either.
oh, look it up.
I'm going to now.
It's fascinating, if only because it's like, I wouldn't. It sounds like something I play in an elevator, but like in a very avant-garde hotel.
Okay.
Something like that.
Okay. Music by mushrooms. Okay.
So in that sense, though, what they're doing, and this is still cool, like I said, there's naturally occurring phenomena in a lot of fungi. Well, they'll relocate ions throughout their structure, so like salts and stuff like that. And that creates localized charge that kind of moves around. And that fluctuation in charge can be used to modulate a sound wave. The same way, I can't remember what that thing is called. It's an old instrument that sounds like ghosts. It's a theremin, that's what it's called.
Okay.
So theremin works the same way. You put your hand in front of a current, and it modulates how the current's moving through the air because your hand's in the way. So that's what they're doing with mushrooms, and it causes the sound to kind of warble in a very, I would say, haunting kind of way as well.
Okay.
But I guess the point of all that is that fungi are full of the components that can make something conductive. They have salts, they have other ions, they have water. So things that can be used to in theory, move electricity around. And also, some fungi have melanin. And melanin has gotten a lot of press lately because it seems to be this miracle molecule that has so many properties. It's this, so melanin, I guess to back up a little bit, is this black-brown pigment that we've all seen before. It's in our skin, it's in our hair, it's found throughout nature. I mean, that's how black labs have their black coloring. It's melanin, ravens, same kind of thing, certain black plants. So it's throughout, it's found everywhere. And what they're finding out about melanin as they dive deeper and deeper into it, it's like, wow, this thing does everything. I think it first started, if I can go on a small melanin tangent, I think it's incredible.
Please.
I think it first started. Well, you opened it up. There was an article a while ago where they were investigating some of the reactor sites in Chernobyl, places that are super irradiated, essentially like anything living, would not be living there anymore because there's too much radiation. And what they found were these black mushrooms, like black as night, inside the reactor. And like, that's weird. Nothing should be alive. What the heck is happening? Like, to be misreaded? It's like, no, it's still definitely irradiated, super rad. But what they theorized is that the melanin in the mushrooms was protecting them from the radiation. And I think that kind of popped open this whole can of worms. It's like, okay, what else can this thing do? A lot. So melanin as a pigment is a protector overall. And I think the community suspects that back before it developed in organisms back when our atmosphere wasn't as protective, with a lot of radiation bombarding the planet, and the melanin was developed to protect us from it, or organisms from the radiation. So it blocks UV light very well, it blocks gamma radiation very well, and that's just kind of the start of it. And somewhere along the line, I'm not sure how they thought to do this, but they found that melanin was conductive as well. So, and that's unusual for a biomolecule to be conductive. And what's kind of the draw or the tie back to the mushroom is that a lot of fungus have a lot of melanin in their surface tissues and throughout it. They can produce like really thick layers of it, which is cool, but I would be remiss if I didn't mention that the melanized ones are actually more dangerous than the normal ones because melanin makes them very virulent and hardy. So a lot of things that we usually use to kill fungi don't work as well on them because the melanin blocks it out.
Oh, okay.
But yeah, so if you see one, this is why black mold is particularly dangerous because like it's very hard to kill. But the one that we work with is totally fine-ish. I'm not worried. So,
well,
it's
go ahead.
Okay. I'm not going on a long tangent, so you might want to hop in while you have it.
No, you're good. You're fine. Okay, as we're wrapping up, what would you like listeners to learn from this valuable conversation?
Ooh, let me think. Well, hopefully I've done my job well and, convinced a few more dozen people not to say dirt anymore and call it soil. But
you'll make them think about it at least.
At least. But I think if I can impart one thing to listeners, it's that soil is beautiful and should be protected. It's this amazing life-giving resource that has, a whole universe of microorganisms in it and some of them can do some really cool stuff. I mean, making electricity is just one of them, but the soil microbiome does so much for us, and it's really underappreciated. So, get out there and every once in a while look down and think about the soil you're standing on and how did it get there? And just more philosophically, like, explore the weirdness of science, Like we were talking about, zapping a mushroom for science, and that's kind of my job now, right?
Right.
As part of that, I'm trying to send electrical signals to a fungus, and I was sending the other day. I was trying to figure out can I send like ones and zeros, like actual data through a mushroom, and I had to pause and be like, my job is weird. This is a weird thing that I'm doing.
Well, I'll go ahead and admit, reading a lot of the information that I was trying to form these questions, I had to read it several times because I'm like, what am I reading? I don't get this. This is weird. What am I reading?
But it's so cool. I mean, sometimes it feels like science fiction. Like one day, who knows, maybe we'll be having this conversation on phones that are wired up with fungus, or maybe we'll be streaming Spotify through a mushroom. I don't know. The future is wild.
Hey, you know what? You put it out there, so there you go.
Yeah.
Well, RJ, this has been so much fun. Again, thank you so much for taking time out of your busy schedule to play with the soil. Notice I did not say the D word. So
I appreciate that.
And again, you've been listening to RJ Jones, a research microbiologist with the Cold Regions Research Laboratory. And we've been talking about sparking the electric secrets of soil. Anything else that you'd like to tell the listening audience before we sign off?
I don't know. I guess just be a nerd. Explore science. There's so much.
So hashtag be a nerd. Yeah, absolutely.
Be a nerd. Like, honestly, you don't have to, as you know, like anyone working at ERDC, you don't have to twist their arm very hard to like talk about their science. And
right.
I think that's how we connect with the community, is like being able to share our stories. And so thank you for doing this. Like,
absolutely.
I think I speak for a lot of people at ERDC where I'm like when this email popped up, I was like, oh no, I have to talk about my research.
Oh.
How awful.
Yes, we did learn when we started this show that, it's not too hard to get people to talk about the things that they do because, again, I tell it almost every show, you can't teach passion, and that's for sure. So